Good afternoon. Welcome to this nice chilly afternoon when everybody comes to class because nobody wants to be outside on a day like this, right? Sorry we don't have a warmer classroom. So before we start, I've something special. You've all seen ChronoZoom here, and hopefully most of you have played with it at home and tried it out. So you're seeing ChronoZoom version 1 that Microsoft Live Labs helped us make, or they made with us last year. We're now hard at work on ChronoZoom version 2, so I'm really pleased. Oscar, would you stand up? This is Oscar Naim, and he's come down to visit from Microsoft. He's the lead software engineer on ChronoZoom version 2, so he wanted to see what we do. Welcome, Oscar. It's good to have you. So when you guys get around to using that, hopefully later at the end of the semester, you'll know the guy who led the effort to make it happen. Great. Okay, so here's where we are in the course. Of the 4 regimes of big history, the cosmos, the earth, the life, and the humanity, we started out by spending 2 or 3 lectures on the cosmic regime. And then we've had some little intermediate things, and now we're working on Earth history, the history of the Earth regime. And we started that out a couple of times ago with the story of the Portuguese explorations and how at least Henrique Leitão, and I think that should be considered the beginning of geology. And then last time we finished that part and then went on and I showed you how geologists learn to read the history of Earth written in rocks. Okay? So now what I want to do is to get on and show you some of the history that geologists have read, mostly by looking at rocks. And we're going to have about 3 lectures on that, and I can't resist having a lot on this because this is the stuff that I do and that I love and that I know the most about. Well, there's an awful lot of Earth history that geologists have read in rocks. How many of you have been down in the Earth Sciences Library in the ground floor? Okay, most of you have. Well, I would guess about half of what's in that library is discussions of what has happened in the Earth's past, written by the geologists who figured it out. So it's a huge amount of stuff that one might study. And, you know, I've been doing it all my life. I don't know but a tiny fraction of what people have learned. So how do we condense that? How do we find some theme that can inform our classes for the next 2 or 3 times? And the way I decided to do it is shown in the title on this mind map that you've got in front of you. Earth history, cycles, eras, and events. So people thinking about history, human history for example, often think about whether it is cyclical or whether it's trend-like. And those views are built into some religions. You know, fundamentalist Christianity is very trend-like. It starts with the creation of the earth and it continues until the day of judgment, and that's a full stop. That's the end of it. There aren't any cycles in it. It just goes from the beginning to the end and then it's over. On the other hand, Hinduism sees history as very cyclical. And all of our lives is cyclical too. You know, you're reborn and reincarnated in another form. So these are 2 ways of seeing history that people have thought about for a very long time. And so I thought it would be useful, interesting to couch our discussion of Earth history in those terms. Is it cyclical? Is it trend-like or era-like? And then there's another thing we could throw in that isn't usually talked about in these other ones, but it turns out to be very important in the study of the Earth and its past. And that is, can you recognize events? Can you recognize big specific events? And obviously for me that's something that's really important because of working on that impact that did in the dinosaurs. So that was one great big event. So we're going to be looking at cycles, eras, and events, and today mostly at cycles. There's a book that I've shown here by Stephen Jay Gould, the great paleontologist from Harvard, that was called Time's Arrow, Time's Cycle. And what he did was to recount how a sort of philosophical thinking about trends and arrows and events underlies the progress that geologists have made over the years. This is an interesting connection here almost between philosophy and science, because it's, to some extent, you find what you're expecting to find. So remember James Hutton? I showed you a picture of his unconformity in Scotland last time. He was expecting to find cycles for philosophical reasons. And darned if he didn't find cycles. And the same thing could be true of people interested in arrows and events. So what I'd like to do, to have you start, just look in the lower half. It says a thought experiment. And I want you to imagine that you were born into a family of European medieval peasants, like the ones in that picture at the bottom. Now imagine you're illiterate, so you can't go and read books. You've never traveled more than a few miles from home. Your entire day, every day, is spent working in the fields. What trends, arrows, and cycles might you recognize from your experience? So what I'd like you guys to do is to pull together into your tables and take just a few minutes and write down some cycles, arrows, and events that all of you medieval peasants might have come across. So please do. Who has some ideas on this now? Yeah.
For arrows, it could be like maturation, so from like being a young child to being
okay, sure. So what should we say that? Maturing or something like that. So you'd see each person going from being a baby to an adult. Yeah.
the seasonal cycles.
Okay, sure. Cycles will be, they'll certainly see the seasons, won't you? Absolutely. What else? Yeah.
Phases of the moon.
Pardon?
Phases of
Moon, sure, that's a good one. I don't remember thinking about that one before. Absolutely, you'd see the phases of the moon. Yeah, Paul?
Farming cycles, harvest, planting.
Okay, sure. So what should we call that? Crops, will that do?
Crop, yes.
We were thinking like a family lineage seems like more linear, like because it's called lineage. So like grandpa, father, son.
Okay.
Like they would probably view plants as more like cyclical because they can watch it like many generations.
I'm sorry, what was the second one? The first.
They would probably view plants as more cyclical.
Okay, so we've got the crops there. So this would be, what should we call it? Family history?
Like a lineage.
Okay. Family lineage. Okay, any others? Yeah.
Like weekly cycle, working every day, going to church on Sunday.
Yeah, absolutely. So, yeah, week with the Sabbath on Sunday.
I love day and night.
Sure. Day and night. Anything else? Yeah.
I think that like your economic status would probably stay the same.
Yeah, that would be almost like a constant. Maybe we should put some constants here. I've never thought about that. That's a good idea. So that's economic status. If you're a peasant, it probably isn't going to change very much. Yeah, Michelle?
if you're, I was thinking like if you're a fisherman, I'm not sure if that applies to your medieval peasants, but it would be like the tides go.
Tide, sure, that's a good one. Anybody think of any events? Yeah.
Marriage, being an event, or like childbirth.
Sure, marriage, birth, that might be. And maybe, yeah? Wes? Yeah, how about that? You know, if the king comes through with his armored knights and they steal all your crops, you probably remember that event. Oh.
If war may have been cyclical, like
Oh, okay.
you would live in the same spot, but different people might control you.
Yeah, I think that's true on a longer viewpoint. I'm sort of trying to think of what any individual could recognize in their maybe 30, 40 years of life. Yeah. What?
Natural disasters like
Okay, sure. Earthquakes, something like that. Disasters. Oh, whoops, that's the wrong place here. Okay. Well, if you notice what's going on here, this one here seems to have a lot more, doesn't it? And if we took the maturing of the individuals and we thought about that for many different ones, you could have the generations or a cycle too. And the point I'm making here then is that it seems like cycles may be the easiest thing for us to appreciate in our lives. There are other things. Certainly as you're maturing, that's a trend, but then it comes to an end when you come to an end. But the cycles are there all the time. Just look at that. The seasons, the moon, the crops, the week, the day, night, the tides, the generations. And so the point of all this is that people have always seen cycles easily. And so thinking about history now, we go beyond our medieval peasants who probably didn't have too much of a conception of history and start going to the more intellectual people. It was easier for them early on to see cycles. And that's just because it generally takes longer for many of these trends to unfold. So let's go, yeah, Brian?
I think it's worth mentioning there's an idea that seeing patterns is kind of hardwired in human psyche as a result of evolutionary selection over time for hunters in particular, but for hunting and gathering. And so if you're hunting rabbits, really hard to hunt rabbits at random, you got to look for a rabbit-shaped pattern, you know. And so we turn out to be really good at seeing patterns. So good that we seem to see patterns where none really exist in a lot of cases. And so I guess I would see cycles as just a subset of patterns.
Wow, that's fascinating. I had never heard that. That's really interesting. Yeah. Yeah, I'd like to learn more about that. That's really interesting. And then that would sort of explain why it was so easy for people to see cycles.
It's easy for us to name them, too.
Yeah. Very interesting. Okay. All right, so now let's go and look on the next page and consider some somewhat more subtle cycles that our medieval peasants might not recognize. And we're starting now to get into what happens in the earth. We've moved sort of from the agricultural community to thinking about the earth. So probably the most easily recognized Earth cycle is what's called the hydrologic cycle or the water cycle. And I doubt if our peasants would know about that. You know, they didn't move very far from where they lived, so they'd probably never seen the ocean. All they knew was that sometimes it rained and sometimes it didn't. And so that's just something that happens. Maybe it's cyclical in that you get more rain in the winter and less in the summer, I suppose. But it's a step beyond that. It's a big philosophical, intellectual step to go beyond that and realize that water itself is cycling through the Earth's environment. So let's look at the picture and see how that works. So you've probably all seen diagrams like this. There are lots and lots of them. But what's going on in that picture is the arrows are showing the pathway of water as it moves through our terrestrial environment. And water will sometimes be in the form of liquid water, and sometimes in the form of ice, and sometimes in the form of water vapor in the clouds. But you can actually plot this out and make measurements. And one of the things that people do in atmospheric science is to think about and measure the fluxes, the amount of water. I mean, in this case, you see underneath in the caption it says the units are thousands of cubic kilometers of water for the storage things. Like if you look in the lower left over there, you see where it says ocean? And under ocean it says 1,335,000 and something. So that is how many thousands of cubic kilometers of water are stored in the ocean. That's the big storage for water, obviously. How much is in the air at any given time as water vapor? Well, up at the top you see it's only 12 rather than 1.3 million. So all of these things can be measured, how much is in storage in different places. And then the transport paths too. So these are showing things like, you see the ocean is evaporating over there, 413, that must be 1,000 cubic kilometers per year that get evaporated out of the oceans. And go up into the sky, but mostly don't stay there because much of that then precipitates. And I haven't been through and checked the numbers on this, but this is a whole field in hydrology and atmospheric science of people who are studying the water cycle, and we have lots of measurements now, so you can see how things are changing. Is this year the same as it was last year, or is it a little bit different? So this is the hydrologic cycle, and it became evident sometime in the Middle Ages to people who thought about this. So Dante, for example, in in Purgatory, there is, one of my Italian friends showed me this, there's a section there in the poem where he actually talks about the water cycle. It's not like he's explaining it to anybody, but he brings it in as an analogy. And of course it's in highly poetic prose, so I'm pretty sure that he understood it. But if you read his poetry, it's kind of obscure. But at any rate, people in the Middle Ages did understand that. Okay, so let's go on and consider now another cycle that Dante could not possibly have understood, because he didn't know what carbon was and he didn't know what carbon dioxide was. Nobody knew at that point. But we now know that carbon gets cycled through the earth. Why are we talking about this? Let me just kind of keep the point fresh in your mind. We're talking about whether history, Earth history in specific, is cyclical or arrow-like. Well, it's got to be cyclical in the sense that it's underlain by these cycles that we know all about. So we're talking about those just so that you get to see a range. I think you'll be surprised at some of the kinds of cycles that we now understand from the Earth. So at any rate, after understanding the hydrologic cycle, maybe the next one that's easy for us to appreciate is the carbon cycle. And you see this sort of crummy diagram that I got off the web there someplace, but it's showing carbon moving back and forth between three kinds of storage. What in this sort of work they call them reservoirs. So on the land there would be carbon stored as in rocks and oil, gas, and coal, and of course in the plants that are living on the land. And then there's some in the air. In fact, every time you exhale in this room, you are adding carbon to the storage in the air. And then, of course, when plants grow, like that plant out there is counteracting you by extracting carbon dioxide from the air. And then a lot of it is stored in the ocean. Some of it is simply dissolved in the ocean water, and some of it is in the form of little animal shells, like the forams that we talked about last time. Those are made of calcium carbonate, so they have carbon in them. So this is the one that is so critical right now, because we're pumping carbon dioxide into the air all the time from burning of fossil fuels. So there's a lot of research that's going on this right now, and there are measurements that are being made all the time. So this is another cycle, a little bit more subtle than the cycle of the water. But now let's go on and think about another one. So there are glaciers. Glaciers are big streams of ice, slowly flowing down the mountainsides. And as such, they are part of the water cycle. There's a certain amount of the Earth's water is stored in ice sheets, especially on Antarctica and in Greenland. So there is water stored as ice, and then that is part of the overall cycle of movement of water. But I'm thinking about something else different here that's different. I'm thinking about the fact that through time, and now we're really getting into history, through time there has been cyclical advances and then retreats of the ice sheets. You know, over the last million years or so, which has been the ice ages, there have been times when Canada was completely covered by a sheet of ice, you know, maybe a mile or two thick in some places. I mean, that's a lot of ice. And especially Scandinavia also. So Canada at that time would look the same way that Antarctica or Greenland does today. Have any of you taken a flight from, say, San Francisco to Europe or back and looked down and seen Greenland? How many of you have seen Greenland from the air? It's a spectacular sight, isn't it? It's absolutely incredible. And Antarctica is like that, only maybe 10 times as much. And imagine, yeah, Natalie? What?
Really tall mountains in it?
In Antarctica, there are places where the mountains stick out. In fact, here, I think you can see them. Let's look over here for a second. So here is Antarctica, and so the blue is the ice here. And can you see these dark bands running through those? Those are the summits of whole mountain ranges, which are almost completely buried in ice. Just the top summits stick out. You can see they're all around there, but yeah, good question. So what I'm thinking about right now in terms of cycles is more of a historical cycle, in the sense that over the last million years or so, there's been this rhythm of about 100,000 years. So 100,000 years cycle over the last million years, in which the ice sheets have advanced, and then the ice sheets have retreated, and then advanced, and then melted away, advanced and melted away. There have been about 10 of these cycles, or something like that, in the last million years. And there's a lot of research going on right now to try to understand what has been the history of these cycles and why have they happened. And it's all tied into climate change. It's all part of the same thing in in atmospheric science and climate science. That's a really big thing. Yeah, Ryan?
Just to remind my section, we talked about Milankovitch cycle.
Yeah, Milankovitch was a Serbian astronomer who figured out that the cycles of the Ice Age match rhythms that have to do with changing in the Earth's orbit, which is probably driving them. So that's another big field in Earth science right now. Let me just show you the kind of cool things that come about in that. If you look in the middle right, there is a plot of ice volume, and in a way that I won't take the time to explain now, you can determine this from oxygen isotopes in 4am shells, right? But if you look at that, this is getting younger upwards. So this is a geologist's plot. That's because it's an ice core and the older stuff's at the bottom. But if you look at, see, ice volume increases to the right. And if you look at the upper half of it, can you see that what happens is that the start at, say, 100,000 years there, and you can see that the ice volume gradually increases, and then suddenly it drops off. And all the way back through here, there's this tend to have these sawtooth cycles in which the glaciers increase slowly in size, and more and more and more, and then they just disappear real quickly. And you can understand why that aspect of Earth history happens, because imagine a glacier ice sheet on Canada is growing. Well, every bit of water that's in that ice had to be evaporated from the ocean somewhere. It had to be carried in by wind. It had to fall and make snow. So it takes a long time to get that much water out of the ocean and onto Canada. So the ice sheets build up very slowly. But if it gets warm, there's nothing that keeps that ice sheet from melting very, very rapidly. So slow build up and rapid melting are typical of what's been going on. Yeah, right.
When there is an ice age and all this water comes in from the oceans, does that change the level of salination within the oceans, and does that have any other effects?
That's not the question I thought you were going to ask, and I don't know the answer to that. I thought you were going to ask whether it changes sea level, and it definitely does. You know, one thing I should have shown you, I meant to, and I forgot when we were up on the balcony having our field trip. You look out at the Golden Gate. 20,000 years ago, there was so much water stored as ice on Canada that global sea level was like 300 feet lower than it is now. There wasn't any San Francisco Bay. The Sacramento River flowed down through what's now San Pablo Bay. It flowed right out through the Golden Gate, and if you'd stood on the Marin headlands then and looked down, you would look down into a valley, and there would have been trees and animals living there. And it's sea level has risen when the glaciers melted. Okay, so all that's going on. Now, what I want to show you is something that's well, let me put it this way. When this was discovered in the 1960s by French geologists in Algeria, they were absolutely dumbfounded. What they found out in the middle of the Sahara, and that's this picture, middle left, you see where it says Ghat, G-H-A-T? They discovered in the area around that, and you can see that's right in the middle, dead smack in the middle of the Sahara, they discovered glacial deposits. And geologists are really good at recognizing the deposits of different kinds of glaciers and rivers and winds and things like that. No question at all. There had been glaciers in the middle of the Sahara in the time period that's called the Ordovician. And recently, there's been even more study of those things. And you can see on my picture there of God, I think I just took that off of Google Earth. And you can see there's a sort of a lineated topography there. And I tell you, man, I've been to this place. We're in the midst of the hyper-arid heart of the Sahara. You know, just almost nothing grows there except at the really rare oasis. And yet you can see these grooves that were formed as a glacier was moving across there. And you know, the glacier would have, there'd be rocks frozen into the base of it. So here's this glacier, and it's very slowly moving along, dragging this big old rock across the bedrock underneath, and it makes these grooves. And this was studied in considerable detail, and the conclusion was that there had been what's called an ice stream there during Ordovician times. So if you look at the one on the right, that's a satellite image picture of part of Antarctica. And what you can see is that there are some low mountains there, just sticking up as we were just talking about. And there's kind of a pathway there. There's a sort of a valley within those mountains. And the glacier, which is on the south side of that, which is actually here at the bottom, is actually channeling through that. I mean, the glacier flows extremely rapidly through that passageway because it's the only passageway around. Basically, the ice is just funneled through there. And, you know, it goes sweeping through there at what, for glaciers, are relatively rapid rates. And so the glacial cycle is not just this 100,000-year cycle that Milankovitch explained, but there are glaciers now. There have been times in the past, like the Jurassic and the Cretaceous, when there weren't any glaciers at all anywhere. And you go back further in time, and there are glaciers in the middle of the Sahara. Does that shock you? It really shocked the geologists when that was found out. So, fascinating things going on. So, if you turn over to the next page now, this is the geological time scale that gives you the framework to understand these things we're talking about. It's not drawn to scale here. It's drawn so the boxes are all the same size so I could write the names in there. But let me just point out the main features of this to you. If you feel like understanding Earth history in some depth is an important part of the education you would like, then you ought to memorize this. And I'm putting it that way because some people won't consider that's a high priority. But if you would like to, or if you're considering being a geology major, that's something that you will learn. You'll need to know it. And so On the left-hand side, you'll see here we have something called eons. Those are the longest periods of time. And you'll see there are 4 of them. The one at the bottom is called the Hadean. I think that's wonderful because when Earth was being hit by big rocks falling out of the sky and you know, there were oceans of molten magma on the Earth, it must have been very hell-like. So this is called the Hadean. And then there are 2 called the Archean and the Proterozoic, and those are times when things had kind of calmed down. You didn't have that rate of infall of big meteorites, and things sort of calmed down. Life got started, but it was single-celled life. And so there's a long kind of fairly quiet interval there that goes from 4,000 million years ago to 500 million years ago. So that's most of Earth history, and most of that was fairly tranquil. And it's, as it says to the right, subdivisions are less clear because fossils are extremely rare. This was before animals started having hard parts that would leave fossils. You know, you can imagine that a bacterium doesn't leave a very good fossil. And so there's just a vanishingly small number of fossils that have been found. But you can't really use those for subdividing the Archean and the Proterozoic. And then at 540 million years ago, suddenly animals started making hard parts, which are shells, and you know, in us it's bones. Why did that happen all of a sudden? Well, I don't think anybody knows for sure, but to my mind, the most attractive hypothesis is that the little trilobites that some of you have seen, these little things that kind of look like pill bugs that on large scale, they developed eyes. And once you had eyes, it must have been a lot easier to get your prey. And so all these other guys who just kind of lived around and hadn't needed hard parts, suddenly the trilobites are running around eating them all up. So at that point, it was advantageous to put some of your biological effort into making shells to protect yourself. So the shells just appear suddenly in the Earth history record, and that's 540 million years ago. And then those are the same shells we talked about last time that are so valuable to geologists for figuring out the ages of things. So you see, now that last 540 million years is divided into all of these subdivisions. You know, first of all, there's Paleozoic, the age of invertebrates, Mesozoic, age of reptiles, Cenozoic, age of mammals. And then those are divided into periods like Cretaceous, which was the last period of the dinosaurs. And then epochs like these ones called Paleocene and Eocene. And it keeps on going down. There are lots of these all the way down to the next level, which is called the stage. So there are hundreds and hundreds and hundreds of these detailed names, and I think it's fair to say that very few geologists know them all. I'd be surprised if any geologist knew all of them. Generally what we do is we learn the ones that are important for whatever we're studying. But there are a lot of them, and if you go on the web, you can find timescales, geological timescales that will have this in more detail or less, as you want.
There's one on the wiki available.
Okay, so what would you look up? Geological timescale, Wikipedia?
It's on the wiki page.
Oh, you mean for the class?
Yeah.
Oh, okay, great. All right. So I'm glad to know that. So check that out. Ryan, were you going to say something? That was what you were going to say. Okay.
Oh, and to also note that rather than tertiary, quaternary, or quaternary, is that different? Some of these the timescales will have slightly different terminology depending on the name.
Absolutely, and it's in a state of flux too, because a lot of effort goes into making and improving this time scale, and so there are people who really devote their careers to figuring out what is the best time scale to use. Okay, so we have that time scale, and now we can work out what happened at different times. Like in the Ordovician, there were glaciers in the Sahara. Okay, so now what I'd like to do with you is to go further into this notion of cycles. Here we had all the cycles that the medieval peasant could recognize. Then we had the water cycle and the carbon cycle that now are understood in great detail. And I don't imagine that anybody in the Middle Ages would have appreciated this or imagined it or could have even conceived it. But we now know that there's a rock cycle. In the same way that the water cycle takes water in the form of liquid or gas or solid ice, and they change back and forth. You know, the glacier melts. That's changing solid ice to liquid water. The same way, it turns out that there's so much time in Earth history that there can be a rock cycle. And you can find lots of versions of this on the web. I put two of them in here. The one at the top is sort of an artistic rendition. And I think it's important to point out here that when you say rock cycle, you don't really mean something like that big sort of a Ferris wheel circle that they've got drawn here. That's really schematic, and I don't know, I guess maybe the artist thought, I'm drawing a rock cycle, I better put a circle in it, right? But a cycle to a geologist, like a rock cycle, is much more of an abstract concept. It really means that there are all sorts of pathways that rocks or portions of rocks called minerals could change through. So let's just take a simple example. Would be supposing you're up in the Sierras and you've got there's granite all around you. Okay, some places when you look at the granite, some of that granite has sort of crumbled down into sand. You've probably seen that, right? And then that sand may get washed down the Merced River down into the Central Valley and deposited there. Now it's become a sedimentary rock. It started out as an igneous granite rock, and now it has become a sedimentary rock in the Great Valley of California. The Great Valley is subsiding over millions of years. More and more sediment gets piled on, and maybe the stuff at the bottom, that's our original sand, now gets heated up and squashed under a lot of pressure. It can get converted into a hard rock called a metamorphic rock. And if it gets carried deep enough, it might even melt and become a new granite. And so that I've sort of shown you a very circular one, but there are all sorts of pathways that kind of cut through from one to other. He's got some of them on there. You see, if you start in the upper right, he's got igneous rocks, extrusive. There's a sort of a sweeping arrow that runs off to the lower left. So this was a fabulous discovery that that the actual rocks of the Earth themselves change in all sorts of different ways that you can think of as a rock cycle. And I suppose you could make the point that the history of the Earth is really the history of the rock cycle. What has been happening in terms of the rock cycle in different places on Earth at different times in the past. So that's one of the things that we're doing. And it then raises a question. Is this really cyclical, or is it really arrow-like? And so what I've tried to show you in the bottom is the idea that you could have one traditional rock cycle. It just kind of goes around and around and around and around. But what we find when we study these things is that there are trend-like changes that happen at the same time. Let me see if I can get a good example of this. Okay, when part of the deep Earth, the mantle, melts and magma comes to the surface, as it does in Hawaii, there are chemical changes that take place in there. You know, the chemistry, there's chemistry going on in volcanoes, right? And if that lava then later gets buried down into the deep part of the Earth and comes up again, that same changes will happen to it again, and they kind of go more and more. It's kind of like you keep refining the rocks through time. And so, I think this is probably a conclusion about all the things we're talking about, is that over time the functioning of a cycle will drive the whole system in a particular direction like this. So I hope you're getting a sort of maybe a subtle view of what cycles are like in complicated systems like the Earth, and that you can't always tell trends from cycles. Maybe the distinction isn't clear. Okay? So I think this would be a good time just for a moment to refocus. Don't start a conversation. Just get ready to go on. Okay, is everybody refocused? I'll accept Michelle. All right, so I want to show you now that we can go further with understanding cycles. We started with the water, then we went to the carbon dioxide, then we went to the rock cycle, and now let's think about plate tectonics. And this is this wonderful theory that was discovered back in the late 1960s and the early 1970s. And it says that the continents are moving around on the surface of the Earth, and that portions of the ocean get subducted down back into the Earth, and they kind of come around over a long time. They reappear someplace else, and they make new ocean crust because the oceans are spreading like that, or the ocean crust is spreading. And so in the early days of understanding plate tectonics, people wanted to understand this business of seafloor spreading, and they wanted to understand subduction, transform faults like we have here in the San Andreas. And over the years, as they worked on this, they began to realize, well, it's not just that that's what's happening, but there have been cycles that have gone on and on and on over time. And so we now think of the plate tectonic cycle. And as it says at the top portion here, fundamentally, plate tectonics is a cyclical process that helps the Earth get rid of heat. You know, there's a lot of radioactive elements deep in the Earth. They are generating heat. And if there weren't some way to get rid of that heat, well, it would just build up and build up and build up. But plate tectonics lets that heat escape. And so probably all of you are familiar with this, but very briefly, the map there shows the present situation, in which, say, if you look at the middle of the Atlantic Ocean, or if you look in the lower center, in between where it says Pacific Plate and Antarctic Plate, those sort of lines with all the little offsets in them, those are the mid-ocean ridges. Those are where deep hot material from within the Earth is coming to the surface and then turning, and the whole thing spreads like that. And remember how some of that heat gets out? Those are the chimneys. Remember the black smoker chimneys that we saw in the Atlantic, and which are responsible for the copper on Cyprus? So that's all part of the getting rid of the heat that's deep in the Earth. And then around the rim of the Pacific, for example, where it says Ring of Fire, that's where ocean crust, which has had lots of time to cool down, cools down, it gets denser, it gradually sinks back into the deep part of the Earth, and eventually it goes around and cycles all the way around through. And it's not a simple cycle, because material is probably flowing from the Pacific to the Atlantic down at depth. It's very complicated, and we're all, those of us interested in this stuff are trying to figure this out right now. What exactly happens right now in terms of the flow pathways, and what has happened in time, through the past. At the very bottom there, I've got a schematic diagram, and this is sort of, this ought to be curved on the surface of the Earth, but it's been flattened out here just to make a diagram that's easier to see. And so you can see where the widest thing where it says plate sort of in the center, and underneath it says continental craton. The craton is an old continental crust. And you can see that's attached to ocean crust, which is the thin black, or the heavy black line. And some of that's going down subduction zone. So this is a schematic view of how plate tectonics works. Yeah, Justine?
Is there a way to figure out what the world would look like when places come into the future and we're trying to see, or is that too...
We're going to come to that, and let me say this. It is possible in theory and difficult in practice to figure out what has happened in the past. To predict what's going to happen in the future, yeah, Matt?
Well, I was going to say, also on the wiki, there's a video of the Earth and how, or one guess of how the continents have been since, I think it goes back 600 million years. And it may go into the future, but you can find video simulations like that online.
Well, this is great. That's this great lead-in, because that's just what we're going to be talking about in a moment. But let me just make the point that you can predict what the Earth is going to look like in 1 million years. I can, you can, anybody in this room can. And nobody's ever going to prove you wrong, at least nobody that you know. So that's safe. Figuring out what has happened in the past, that's difficult, and we're going to see more about that, because that's something that I find absolutely fascinating. So if you turn over to the next page, now you'll see another cycle. And this one's even more abstract, or even grander, let's say. This is the supercontinent cycle, or sometimes called the Wilson cycle. It was named after a Canadian geophysicist whose name was J. Tuzo Wilson, who was the first person to understand that this was happening. So remember, water cycle, you can watch it happen today, for example. Look out at the rain. Carbon cycle, rock cycle. Now we're talking about something that's even more, even farther from our day-by-day experience, and that is the supercontinent cycle. So look at what's going on here. This is a diagrammatic version to show what's happening. So you start at the top. This diagram here is showing part of a continent. And continental crust, that's rocks that are things like granites. And it's usually about 35 kilometers thick, about 20 miles. 20 miles, not here because we're in a different, if you went to Iowa, 20 miles down, you'd come to the bottom of the continental crust and you'd get into what we call mantle. And what's happening in this first diagram up here, the one labeled A, is that continental crust is beginning to crack. Something is starting to pull it apart. So you can see those sort of fractures going through it schematically, and then that's a little volcano there. That means that deep, hot magma from depth is able to come. This is the beginning of the breakup of a continent. Okay, then in the second diagram, you can see where that breakup is really getting going now. And so those are no longer just cracks, they're faults in which the crust is actually in the process of tearing apart and breaking apart. Anybody know where on Earth this is going on right now? Pardon? Africa, exactly. So look, here's Africa. See the outline of Africa: West Africa, South Africa, East Africa, and there's Saudi Arabia right there. Well, right down through here, through East Africa, is the area that's called the Rift Valleys. And this is a place where the eastern part of Africa, right there, is in the process of breaking off and moving over to, it's going to go off this way, and there's eventually going to be, probably, this is my prediction, there's eventually going to be an ocean between there. And in fact, let's see, is it eastern? Yeah, that's still the best map we have. I guess all the colors will make it a little confusing. That's the Red Sea right there, and see, Arabia has pulled away from Africa, and then the Gulf of Aden is down there. So this is actually going on right now. Africa is in East Africa is in that stage B on this picture. The continent hasn't broken apart yet, but it's getting there. It's working on it. And then the next one below, in number C, what is portrayed there is that now the crust has really broken apart, and you're starting to get ocean crust in between, and ocean there. And so that's the situation that the Red Sea is in at the present time. So remember, picture over there, it's kind of a long, narrow sea. And so in that case, the continent has pulled apart far enough for the ocean to be there. Now, if it continues as we go on into the middle, the wide one, D, now we've got a whole ocean there. And can you see? Here's a whole ocean right there. See, Africa used to be right next to eastern North America, this part of Africa. And there was a time when that was continuous continent all the way across there. And then the two parts began to separate, and you got something that looked like the East African Rift Valleys, and then something looked like a narrow Red Sea, and now it's opened up into a whole wide ocean. And that's where the seafloor spreading is taking place. Well, I think you can picture that on a sphere, you can't do that indefinitely. If this is a sphere like the Earth, and you start spreading things apart here, the ocean can't get bigger indefinitely, because at some point the continents are going to collide on the other side and it's going to stop. And so that's what's going on here in E and F, is you're starting to have a subduction zone, because some of that ocean crust is now starting to sink back into the mantle. And that's what's going on around the Pacific. So for example, up here in the Aleutians or in the Andes down there, in the Andes, this ocean crust right here is moving towards the right, toward the east, and it's subducting under the Andes and making all of those big volcanoes. And if you have subduction go on indefinitely, eventually the continents on either side of the ocean will collide. And that's what you can see going on in F. The continent on the right is approaching that subduction zone, and in G at the bottom, you've had a continental collision, and those two continents that used to have an ocean between them are now jammed together. And so you've formed a new continuous continent. Anybody know where that's gone on? Himalayas, exactly. So if you look at that, again, hard to see on this map, but there's India, and here's Asia, and these are the Himalayas, and those are the highest mountain range we have on Earth. And it's there because India used to be down here, and India has moved north. And about 40 million years ago, it collided with Asia, and it keeps on colliding and pushing up the Himalayas mountains. So now you see at the bottom, if we eroded that off, we'd be back to where we started. So we went from a continuous continent, the continent broke apart, and now then it has come back. Maybe not that one, but some continent pieces have come back together. So that is the supercontinent cycle, and it's probably the grandest cycle that we know of on this planet. And curiously enough, it doesn't seem like there's plate tectonics on any of the other planets. We thought there would be at one time, but there isn't. Okay, so now what I'd like to do with you is to show you some more what really happens. The previous page was a very diagrammatic simplification. Let me tell you, right now, one of the most exciting fields in geology is doing just exactly what I think Justine was asking about, is figuring out what the history of the continent cycles, the supercontinent cycle, has been all the way back in time. A lot of geologists are working on this, and geophysicists and geochemists. To my mind, it's about as interesting a thing as there is, but I'm a geologist. So look, on this next page, if you look in the upper left, you'll see three maps, and they were drawn by Alfred Wegener, and he was the German meteorologist. Remember, we saw a picture of him early on. He was the German meteorologist who, back in about 1912, I think, had the idea that continents had been drifting. And he was beaten down by the geologists at the time, who thought that all continents had always been exactly where they are today. But his drawings there, the upper one shows the way he thought things were probably about 250 million years ago. And then the middle one would be where they were about 100 million years ago, and the bottom is today. And what you can see in the upper one, there's almost no ocean. There's just a little bit of ocean between Africa and North America. But then that ocean and all the others widen when you get to the middle one, and then they continue widening. He didn't get it quite right, but good Lord, he was the first person to do it. You wouldn't expect it. Can you see on the maps to the right, those are more modern ones. They're highly simplified. But in Pangaea, by the way, Pangaea means all the lands, and it's the name that Wegener gave to this supercontinent that he inferred that had used to be. And what you see, I've labeled there Tethys. Tethys is this sort of a great big gulf, a great big indentation on the eastern side of Pangaea. And it's curious, if you look over at Wegener's pictures, there's no Tethys there. But he didn't have the tools we have today for actually using the computer to move continents around on maps and see how they fit. But there's this modern version that shows what's happened in the last 250 million years. Okay, here's a useful point, I think. We can go back to about 250 million years with considerable confidence. If you look on this map, you see the ocean. The ocean has these sort of stripes on them. Those are stripes. The stripes mark oceans that formed in particular time intervals. And they come from marine magnetic anomalies. And I have to point out, because it means a lot to me, that we used to be at New York at Columbia University's Oceanographic Lab, and Millie actually drew the very first map of the age of the ocean basins that anybody ever drew. This is more advanced now, but that was pretty cool. There was a while when she was better known in geology than I was, because she'd drawn that map. But at any rate, you see, this portion of the continent in this dark green is the ocean, is the same as this portion of the ocean. When I say ocean, I always mean ocean crust, all right? We're talking about the rocks, not the water. And so there was a time when none of the stuff from the light green through the orange to the other light green had existed yet. So this portion and this portion were next to each other. And so we can actually move the pieces back, and you know where they were, all the way back to 250 million years ago. That part is basically solved. You know, details to work out, but it's basically solved. Now, if you want to see what happened in the cycle before that, it's much, much harder, because there isn't any ocean left. There's none left. So we don't have any of those nice age stripes to help us figure out how things went. And so figuring that part out from 250 million years ago back to about 1,000 million years ago, that's the active research field right now, on which probably hundreds of geologists from countries all over the world are working on right now, trying to figure that out. But that represents an entire cycle of the supercontinent cycle, from ending up in the supercontinent that Wegener figured out, which is called Pangaea. If you track back in time, there's a lot of ocean, and then before that, there was an earlier supercontinent that we call Rodinia. And it's very hard, still at this point, to reconstruct Rodinia with any confidence. You know, we are starting to get a general idea of what Rodinia was like. But then, starting from Rodinia is a supercontinent. It's all the continent pieces together. It breaks up into continental fragments, and then those continental fragments recoagulate to make Pangaea. Is that all clear? Any questions about this at this point? Yeah, Michelle. If we go back to when there is when no ocean is left from those times before 250 million years, you can use paleomagnetism. What you try to do, and I'm show you an example in a moment, is to say, here's a piece of continent that has a particular kind of rock on it, and this other continent has got the same particular kind of rock from the same age, from age dating. They were probably next to each other. But it's done with much less precision and reliability than matching those age stripes. Yeah, good question. Okay, so now if you look down there at the bottom, here is a very simplified map of North America. You can see Florida in the southeast. And this is the way things were, say, around 1,000 million years ago. This was part of Rodinia. And you'll notice that California is sadly lacking there. Wyoming is right next to the ocean. And those unfamiliar names, Yavapai, Mazatzal, those are parts of Arizona. So there wasn't any California there. All of California that we live in has been constructed since then. It's brand new ocean crust. And so California is not part of old North America. It's a later accretion, a later addition. And so for a long time, people thought, well, what used to be where California is now? And people looked at all sorts of places. They looked at China, they looked at Siberia, South America. What could it be? Remember, we're trying to get back beyond 250 million. We're trying to find out what Rodinia was like. Well, that guy that you've met a couple of times already, Eldridge Moores, the one who took Millie and me to Cyprus, he had the key idea. And he had it when he had done a lot of work in Nevada, so he knew what the western edge of North America was like. He went on a field trip, a remarkable field trip, to Antarctica to look at the rocks that are exposed in those few little mountaintops that we saw around there. And he was absolutely blown away. He was seeing rocks in Antarctica that looked just like rocks he knew from Nevada. So he was the first guy to propose what became the key for understanding Rodinia, and that is that what used to be where California is now is Antarctica. Can you imagine that? Maybe today it almost feels like it, but can you imagine that we are sitting now where Antarctica used to be? Yeah, that still blows me away. And there's a lot of debate on it. You know, that was the first initial idea, but it was on the right track. So if you turn over to the next page, you'll see something about that. So in the upper diagram, there is a map of Rodinia as it was pictured in 1991. Things have changed a bit since then, but it's still generally on the right track. Let's look at that map. This is an attempt to put together what Rodinia looked like 1,000 million years ago. You know, the supercontinent from before Pangaea. So let's look at it so you get familiar with it. In the center, do you see where it says Laurentia? Okay. And I think you can see Hudson Bay, and you can see the Great Lakes there. So Laurentia is a name that geologists like to use for the ancient core of North America. And it's called Laurentia because the St. Lawrence River in Canada flows kind of right through the heart of that land. So when you see Laurentia, we're talking North America, although not California. Because if you go sort of northwest from where it says Laurentia, do you see East Antarctica there? Okay, that's what Eldridge figured out, was that East Antarctica had been adjacent to Laurentia. And as I say, there's still controversy about that, but something like that is almost surely right. And you can see how that kind of gray, dark gray band sort of wraps around East Antarctica and then continues down into Laurentia, where it says TX, that's Texas. And then there are other pieces around there. Can you see that Siberia is over there next to North America and Greenland? And then there's Baltica down in the south. See, Baltica, you can sort of see the shape of Scandinavia there. This is for you. You can see Sweden in there. And then there's Amazonia. That's part of South America. Can you imagine a time when the Amazon was right next to Norway? Well, that's Rodinia, folks. It's different. And then there's West Africa and the Congo and Kalahari. Those are all parts of Africa now, but they weren't then. They were all part of Rodinia. And there's India, and look, you can see Australia is up next to East Antarctica. So this is a 20-year-old version of what Pangaea, what am I saying? Rodinia would have looked like. You know, we got better maps now, but this still, I wanted to show this because it shows so clearly then what happened. So now, if you go from that one, up in the upper right it says 700 MA. Remember, MA is million years ago. So that's a plot of Rodinia as it was just about to start breaking apart. Yeah, man?
Are there any like reliable, like solid ways to estimate the climate?
Oh, absolutely. That's something. Paleoclimatology is something that geologists do. I mean, if you find coal in a particular place, you know you had humid, swampy climate at that time. If you find fossil sand dunes, you know you were in a desert. That's very well. There's a lot of what's down in that Earth Science Library is that kind of plot.
So the heat from the center of the Earth is generated.
It's making this take
So
place.
as you go further back in time, closer to the formation, shouldn't this be like speeding up as we go backwards, or should it be slowing down through time?
You would think so, but I think what has actually happened is that what you suggest is exactly what was happening at the very beginning when the Earth was very hot. But the Earth is now probably pretty close to a steady state, which means that the rate of heat production by radioactive elements in the interior is balanced by the rate at which the seafloor spreading is taking place. Most people, I think, would feel right now there's no big differences, no big changes going on. Yeah, Ricardo?
Are there any accurate predictions on how the Earth will be like in another 100 million years?
Well, there are predictions, but how accurate they are, I don't know. One of the things that you find out if you study plate tectonics in detail is you'll find out that whatever pattern is going on now cannot continue. It can maybe continue for millions of years, but it can't continue for 100 million years. So that means that the San Andreas Fault will live its life, and then it will stop, and some other plate boundary will take place. Okay, Josh?
Going back just a little bit, the Earth gets rid of.
Mm-hmm.
So is there any sort of looking at the relation?
Probably not, because we're talking now about the very slow release of a rather small amount of heat that's generated in the interior of the Earth. And there's a second completely independent system which is driven by the heat from the sun. And that's what drives all of the climate on the surface, including the glacial cycles. So I think they're probably not related. So let me just go on, because I want to make sure I don't miss the chance to show you this thing. So look, we have Rodinia as it was at 700 million years ago. And now, in the lower half of the page, we've gone to 500 million years ago. And you've got a situation where Rodinia has broken up and then gone to form something else. So look, you can see Laurentia in the middle in the upper diagram, and then on the lower diagram if it's off to the side, right? And Baltica has kind of come off. And then what's left, the big collection in the lower left, is not just the rest of Rodinia. It's Rodinia rearranged to become Gondwana land. And Gondwana land, maybe I haven't used that term, that's all the southern continents. So if you look over there, South America, and then Africa, India, Australia, and then Antarctica at the bottom. All of those together form Gondwana land. So what I want you to do now is to look in the lower left. Look very carefully. Can you see those familiar continents in there? Can you see South America? Can you see India? Can you see Africa? Because they're supposed to be in there. That's Gondwana land. Anybody see them? Yeah. If you turn over on the next page, you'll see what happens is Gondwana land is there, and the reason it was hard to see is that it's upside down. Go back to the previous page for a second. Look at the one on the bottom of page 9, bottom left. Now, if you take that, just take your hand out and turn it upside down. Now you can see. On the left, there's South America, and then you can see Africa that has West Africa, Congo, and Kalahari. See India sitting in there? Can you all see that? Okay. So what that means, and now we're on the last page, that means that when Gondwana land formed, it was upside down. North was pointing south. Let me do it this way. So imagine my fingers are pointing north, and here's the globe. We're kind of looking through. And it was actually like that when it formed. North is here, and all these modern norths were pointing south. So the question is, how did it get to its present orientation? And your first thought would be, well, it twisted around like that, right? That's not how it happened. What happened was that it drifted down, it moved as a continent under the South Pole, and came up on the other side. So now all of those norths are pointing north. Isn't that cool? So then, what you realize is that means that Gondwana land, which was upside down, passed under the South Pole and came up the other side. Is that starting to make any sense? So that means that if you think of it from the standpoint of the Earth, Gondwana land went around and came up the bottom. If you think about it from the standpoint of Gondwana land, it means that the South Pole passed right over Gondwana land. Guess when? In the Ordovician. In the Ordovician. Remember what happened in the Ordovician? That was when the glaciers formed in the middle of the Sahara. And so now you can see why those French guys who discovered those glacial deposits in the 1960s were utterly mystified. Because in the 1960s, early 1960s, geologists didn't believe in plate tectonics. They didn't believe in continental drift. So to a geologist of those days, if it was in the Sahara, which is in the middle of the driest place on Earth now, it would have been in the Ordovician too. And so it was plate tectonics, by showing how the continents move around, that explained a movement, and that actually the South Pole was actually in the center of Sahara in the Ordovician, and that's where those glaciers came from. So I've always thought that that was a wonderful story. And I think what you might conclude at this point is that Earth history is fundamentally cyclical. Cycles rule in Earth history. And to some extent, yeah, right, they rule, right? Except that if you come next week, we'll find that there are interesting trends as well. Thank you all. We'll see you next week.